So today we'll be talking about impact, central impact, and oblique impact. And really, I'm going to spread this over two classes because we have an extra class. Okay, so this section is on impact, and there are two types of impact. One, and there are many impacts, but the ones which we'll study in this is central impact. Okay, central impact is, well, one example would be a head-on collision. If somebody is traveling on the wrong side of the interstate, that would be a head-on impact. The other impact we'll be studying is what is known as oblique impact. This is what you might likely see if you're on a stop sign and if two cars are traveling at directions which is not aligned, then you'll have an oblique impact. Okay, so first we'll talk about central impact and develop the equations, and then we'll talk about the oblique impact. So let me draw what I would call a central impact first. So we'll assume, so this is a chapter on particles. So really these circles don't have much meaning. They're really point masses. Okay. So 2 point masses colliding such that their velocities are in the same direction as the impact. So this is called the line of impact. That's the direction along which they're impacting, and velocity V and VB is the velocity of the two masses. Okay. So typically, what sort of thing you might expect in such a problem is you know the velocity of the two masses before impact. Okay. So let's call them VA1, VB1. Velocity before impact. And the question is, find the velocity after impact. So these are typically the knowns. These are typically the unknowns. Okay, so clearly, what's the velocity after impact? What will happen if a truck collides with a car or a motorbike collides with a truck? What's going to be the velocity after impact? That's what we're most interested in. So since we're interested in two quantities, we need to generate two equations. The first equation is called conservation of linear momentum. Okay, so what we'll do is say that MIVI1, where I would in this case would be A and B. It doesn't have to be just A and B. It could be more than two particles, but we'll only in this course we'll typically look only at two particles. So MIVI1, that is the one indicates before impact, equals the sum of the momentum after impact. So VI2, I equals A and B. This is after impact. Now that equation is one equation which has both these unknowns. So one equation will not be able to solve for the two unknowns. So we need to generate another equation. Now the other equation comes from what is known as coefficient of restitution. Okay, and this particular formula which I'm going to write is an empirical formula. It is derived from experience. There's no, it's not just like friction is an empirical formula. Why is it mu times n? Because somebody did an experiment, figured out that that describes the friction for most objects. That's how the formula came about being. So coefficient of restitution is defined as velocity of separation divided by velocity of approach. I'll just give you what that means, velocity of approach. So the book defines this E as follows: VB2 minus VA2 divided by VP1 minus VA1. Okay, so everything above is velocities after impact because of the two. Everything below is velocities before impact. Okay, that's why it's called velocity of approach. It's the difference in velocities of B and A. I think I made a mistake here. This should be V. Yeah, should be swapped. Okay, so this is the difference in velocities of the two masses before impact divided, and on top is velocities after impact. Okay, so in this case you would be given this. This is usually given. This is equation 1. Call that 1, and this is 2. So 1 and 2 are the two equations in two unknowns, VA1 and VP1. Sorry, it's VA2 and VB2, velocities after impact. So given those two equations, you can solve for the two unknowns. Okay. Now I think it's very confusing to write this as B minus A minus B. The way I like to write this, and it's really easier to remember, is always write it as, it's up to you if you want to write it this way. So I like to write minus E equals VB2 minus VA2 divided by VB1 minus VA1. Okay, what I try to do is, just so that I always do B minus A, I just switch the sign over here, I just put it minus E. This is, I think, easier to remember than trying to remember this. But it's up to you, you can write it this way. This is how the book defines it. I just try to remember it like this. Okay, so let's talk a little bit about a coefficient of restitution E. Okay, this is E, and then let's solve some problems before we go to the central impact, sorry, oblique impact. Okay, so E, turns out that E has only some values. It can take a value of 0. Okay, what does E equals 0 mean? It means that 0 equals V VA1 minus VB1 VA2 minus VB2. It means that velocity after impact of A is equal to velocity of B after impact. Okay, this is also called as plastic impact. Example, if you drop a ball and if the coefficient of restitution is 0, then this says that A is the ball, B is the ground, velocity of the ball is going to be velocity of the ground, which is going to be 0. So it's going to stick to the ground. The other extreme case is E equals 1, which is an elastic impact. Okay, what that means is if I drop a ball which is perfectly elastic from a height h, then after the bounce, it will come back to height h. So the most, in real life, real world, you will usually see E to be between 0 and 1. It can take a value of 0, that is the ball or whatever you drop sticks to the ground, right, at 0, or it will be less than 1. It will never be greater than 1. What does it mean to have E greater than 1? It means that the energy of the system is increasing. So it means that the energy of the system increases after collision. Okay, this one means energy is conserved. In this case, it means energy is dissipated. So when E is anything less than 1, energy is dissipated. So our experience says if you drop a ball from height h, it'll jump back to a height which is less than h. That is energy dissipated. E equals 1 means if you drop a ball, it comes back to the same height. The energy is conserved because it started off the same energy, it ended up with the same energy, which is potential mgh. And then if E is greater than 1, then it means that if you drop a ball from height h, you jump to a height greater than h. That's not possible. However, I know one case where it's possible. Okay, there was an entire movie made on this. Learn and solve a problem. The 0.5 kg ball is fired from a tube A with a velocity of 6 meters per second. If the coefficient of restitution between the ball and the surface is 0.8, so this is 0.8 E. Determine the height h after 8 bounces off the surface. So you're going to find this height. Okay, so let's think of it backwards. If you want to find the height h, then we want to know what is the velocity with which this is going off, right? Or if we can find the vertical velocity, then we can use the formula of v square at v square minus equals the velocity over here, which is velocity over here is 0 equals velocity over here plus velocity square over here is velocity square over here plus 2ah, right? We could use that. So we need to find the velocity over here. How can you find the velocity over here? We need to find the velocity after impact. So we need to know the velocity before impact. If you know the velocity before impact and we know the coefficient of restitution, we can find velocity after impact. So let's find the velocity before impact, knowing that the particle is going to move as a projectile from A to B. Okay, so my goal is to find velocity at B before impact. Okay, so how can I do that? So I can use the equations for a projectile, clearly. I know that the height from A to B is 2. So maybe I can use, so since I know the height and I know the velocity, I can use the relation between velocity and height, which is velocity of y square is velocity, we call this x, this y, so velocity y 0 square plus 2gh or 2a acceleration times delta y, right? So the velocity at B equals velocity at A, which is 6 square. No, that's not right. It's the vertical velocity, so it's 6 sine of 30 degrees square Vy 0 sine of 30 degrees plus 2 g is 9.81 downwards and upwards is positive and delta y is downwards, so both are negative. P, what's that? Let me write it as Py at B squared. I just want to say that this is the velocity here. Vy B. Okay, so one equation, one unknown, V by B is 6.94 meters per second. Okay. Okay, so I know the velocity before impact. Now let me try to find the velocity after impact. For that, I need to use the coefficient of restitution. Velocity after impact. So the definition of E is velocity of the two bodies involved in the collision. So one of the bodies is the particle, the other body is the ground, right? So velocity of, let me call that particle after impact minus velocity of ground after impact divided by velocity of particle. Let me write this as Vy. Vy 1 minus velocity of ground before impact. Okay. Now the ground does not move, so these velocities are 0. So minus 0.8 equals velocity after impact is unknown. Velocity before impact is known as 6.94. So Vy 2 equals I think I made a sign error here. This should have been negative. To be very, if I assume upwards to be positive and downwards to be negative, when I solve for Vy, I would get this 6.94 would have two signs, right? Plus and minus. I need to take the minus sign because upwards is positive, downwards is negative. So I would stick to the negative sign. I forgot to add that. So now I would have minus 6.94. So 6.94 times 0.8 is 5.54 meters per second. So comes out to be positive because clearly the velocity after impact is going to be upwards and not downwards. Now analyze motion from B to C. So in order to find out related motion from B to C, which is here to here, I can use the same formula I used earlier. Velocity at C square equals velocity of B square plus 2a delta y. Velocity of C, since it's the highest point, is 0. Velocity of B is 5.54, which I just found, plus 2 times gravity is downward, so minus, and delta y is upward, so positive h. So if you solve for h, since that's one equation, one unknown, you get 1.57 meters. Okay, so this is motion from A to B, this is motion at B, and motion from B to C. From A to B, at B, from B to C. So that's how you solve this. But here's something else, which is, if you see this question involves what you learned in the first chapter I taught, chapter 12, as well as chapter 15, right? So let's look at oblique impact. So this is the line of impact, the line which joins the center of the two particles. Okay, let's call this line the x-axis. Okay, that line is 90 degrees to the x-axis, so it's the y-axis. Okay, so what makes it an oblique impact is, let's call this B, let's call this A. The velocity of B is at an angle to the line of impact, and velocity of A is also at an angle to the impact. So this is, let's say this is theta A. Okay, so this is like if you're in a stop sign and if two cars are traveling at an angle, that's kind of the collision you see. They will not, after colliding, they'll spring and go in different directions. If you have a head-on collision, they'll spring back in the same direction, right, of the impact. Okay, so the question is, what are the knowns and what are the unknowns? You typically know the velocity of both the masses before impact. So the velocity of A in the x direction before impact is known. Velocity of A in the y direction before impact is known. Velocity of B in the x direction before impact and velocity of B in the y direction before impact are known. You're also told the coefficient of restitution, and the unknowns are velocity of A in the x direction after impact, velocity of A in the y direction after impact, velocity of B in the x direction after impact, and velocity of B in the y direction after impact. So 4 unknowns. 4 unknowns. So we better generate 4 equations to solve for the 4 unknowns. So the question is, how do we get the 4 equations? So we need 4 equations. Solve for the 4 unknowns. So here's how you get the 4 equations. So conservation of linear momentum for both particles about the line of impact, which is the x-axis. So when you do that, we get m a v a x plus m b v b x. Write it differently. V a x before impact, v b x before impact is m a v a x after impact plus m b v b x after impact. Okay. So momentum before impact, which is denoted by 1s, equals a momentum after impact. Second is conservation of linear momentum for individual particles about y-axis. Okay, what this means is the mass of A times velocity of A in the y direction before impact is mass times velocity of A in the y direction after impact, and mass of A mass of B velocity of B in the y before impact is mass of B velocity impact. Okay, this one is slightly hard for people to believe. It just means that if you take A, if they're colliding this way, along the y direction, you can just take the momentum of the first one, and equate it to the momentum of the first one after impact. There's actually an assumption here which people miss. The assumption is that there is no, so when there's impact, we always assume that the forces which take which act between two particles are along the line of impact. So when they're colliding this way, the line of impact is that way, and so there's a force that way. There's no force in the vertical direction, so there's no impulsive force in the vertical direction. That is why this is true. Okay. Now in real life, this may not be true in certain cases, but if the particles are smooth and they are circular like they've shown, then that's a good assumption. So that comes with caveats, but that's what we'll use. So 3 equations so far. We still need one more equation because there are 4 unknowns. The last one comes from coefficient of restitution. Which says that I'm going to write it in my way, which is minus E equals velocity of separation Vp, and this is only true in the x direction, Vbx, that's after, and Vpx before, Vax before. So 1, 2, 3, 4 are the 4 equations to solve for 4 unknowns. Vax to Vay to Vbx to Vby2. Okay, so next time on Friday we will see how to apply, use this what we learned and solve 2 problems. Okay, I'll see you on Friday. Remember that the last exam is on Friday next week. Okay, and it covers, I think, not this chapter, but chapters 14 and 18.